me briefly introduce Lenté Dreyer. So she's a graduate student from at the Northwestern University in Potchefstroom, and with Marcus Böttcher. She made her Master of Science in 2018-2019 and wrote a really nice thesis on Monte-Carlo simulations of polarization-dependent Compton scattering. I actually kind of was one of the on their committee for that thesis, and was a beautiful summary of the state of the art, and had also really good results. And now she's doing a PhD student using this code to develop strategies for observing blazars with optical X-ray and gamma ray polarization observations. She just said she will do her PhD in November 2022. Do you want to start?
Yes. Can you hear me and see my screen?
Yeah.
Okay, good. Okay, so thank you so much for the introduction. So today I'm going to talk a bit about the science drivers for high energy polarimetry. So in particular, the scientific potential and the modeling of high energy polarization in astrophysical jets. So it would be with a special interest in blazar jets, but I try to touch as many sources as possible. Okay, so this is a plan for the talk. So I'll talk about the scientific potential of the high energy polarimetry throughout. So polarization carries important information about the astrophysical environment in terms of how the magnetic field configuration links into the acceleration of the particles and the energetics of the particles. So high energy polarimetry would provide constraints on the geometry and the structure of the astrophysical source. So there's a lot of physics in play here when we talk about high energy polarimetry. So sometimes it's helpful to group those the physics into 4 categories. So a lot of review papers do this as well. So this was actually the specific groups from Fabiani 2018, and I found it very helpful when I do my research. So throughout the talk, I'll try to group the physics that I'll talk about into these 4 groups. And then in between, I will also talk about the polarization-dependent modeling. So what we have as tools for predicting the polarization in the high energy regime of these sources, and how we can provide the strategies combining the optical X-ray and gamma ray polarimetry to get more information about these sources. So let's jump right in. Why doesn't it want to? Sorry. Okay, there you go. Okay, so I selected a few polarimeters in X-rays, hard X-ray, well, X-rays and gamma rays, and then I tried. So throughout, I'll try to group them in terms of what the science objectives of these polarimetry missions are as well. So underneath here, you'll see the polarimetry missions, and when I talk about a source, the polarimetry mission will just go red, so that you know there will be in the future, and there was also in the past, polarimetry missions that will be able to observe and measure the polarization in these sources. Okay, so the groups that I talked about, the physics, what we can learn from high energy polarimetry is the radiation mechanisms, particle acceleration, the source components, so the origin and the structure of these sources, and fundamental physics as well. So obviously the physics that we learn connects with each other, but it's sometimes useful just to have these groups on the sideline. So with radiation mechanisms, I mean what I what I mean by radiation mechanisms is what the origin of the high energy emission is from these astrophysical sources. So we'll get to that in a minute. And with particle acceleration, I try to answer how do astrophysical sources and jets accelerate these particles in the high energy regime. And of course, for the sources, we just, as physicists, we like to know what the origin and nature is of these astrophysical sources. So I tried to, so I'll talk about a few prospects in each of these groups. So for the radiation mechanisms, I'll talk about the high energy emission from blazars, GRB prompt emission, and then I'll also just say one or two things about black hole, X-ray binaries, pulsars, and magnetars. For particle acceleration, I'll concentrate on the particle acceleration in blazar jets, and the jet emission region as well. And then I'll just say some few things about the source components, the global jet structures and blazars and GRBs, the origin or the geometry of the corona and radio-quiet AGN, so black hole X-ray binaries, and that will tell us more about the origin of the corona, the geometry of the torus, and polarimetry can also give you some ideas of how to measure the black hole spin. And then you can also have some we think that we can have, we can constrain some things about fundamental physics, which include quantum electrodynamics from magnetars and neutron stars, polarimetry from that, general relativity, and quantum gravity from blazars. So for magnetars, pulsars, pulsar wind nebula, and supernova remnants, so I just put it in here for reference, but I won't go into detail from it because I don't know a lot about this. But for the radiation mechanisms, the hard X-ray tail of the emission from blazars is still under investigation, and a very popular model now is resonant inverse Compton scattering. And then emission mechanisms from isolated X-ray pulsars is also under investigation, and that can also be answered with polarimetry, with high energy polarimetry. And so these are just this is a schematic picture of these three possibilities. So the radiation can originate directly above the polar cap, so the polar cap model. And then you have the radiation originating in the outer magnetosphere, so the outer cap model. And then also you can have the radiation all the way from the polar cap to the light cylinder along the last open field, which they call the slot gap model. So I don't know much about these models, but polarimetry can help us to distinguish between these models, since it depends on, phase resolved polarimetry can test these models and can help us to understand the emission sites and the emission mechanisms in this isolated X-ray pulsars. And then you also have a few models on acceleration mechanisms and supernova remnants and pulsar wind nebula, and also you can maybe test the quantum electrodynamics from magnetars as well. And the polarimetries in red here is, I guess there can be the other polarimetries can also maybe measure it as well, but these polarimetries in red specifically mentioned magnetars, pulsars, and supernova remnants. Okay, so into something I know a little bit more about. So black holes and X-ray binaries is also a very popular science objectives for the polarimetry missions, because they have a very strong magnetic field, so they are good sources to observe high energy polarimetry with. So for them, you want to know what the origin of the high energy emission is from black hole and X-ray binaries. So, recent findings of the high energy polarization measured for Cygnus X1 suggests that the jet origin of the X-ray hard X-ray emission from X-ray binaries, but multi-wavelength ACD's modeling of the Cygnus X1 X-ray binary predicts insignificant contribution of the jets and hard X-ray. On the other hand, the studies reported suggested that radiation from hard X-ray emission from these sources can originate from leptohydronic corona due to synchrotron emission. So they predict radiation. So the radiation for this model predicts higher polarization, and this the polarimetry. The polarization predictions for this model is also independent of the states of the X-ray binary, which this synchrotron origin would be dependent on the states. So careful polarization measurements of black hole systems in both the hard and soft states will then give us more information and lead to a proper understanding of the origin of hard X-rays in these sources. Okay, so this links also into the origin of the corona as well, and the geometry of the corona. And for that, we have most popular two models, the slab model and the disk lamppost model. So for the slab model, the polarization would be higher. So for polarization-dependent modeling, you have a lot of options for to model the polarization for different scenarios. So for the origin of the high energy emission from black hole X-ray binaries, this is a very good example. So a code called RADPOL. And I'll get to the polarization dependent modeling in a bit. I just want you to have an overview as I go along in the talk. And for the origin of the corona and the structure of the components of black hole X-ray binaries, there's also a lot of codes that was developed in order to give us some predictions of the high energy polarimetry for different models of the corona. Okay, so gamma ray bursts is also a very popular field for polarization, and they are also the sources that we actually do have polarization measurements for. The polarimetry emissions for gamma ray bursts is usually just for gamma ray bursts, so they concentrate on gamma ray bursts. So I always think that observing and predicting the polarization of gamma ray bursts is sometimes in their own league. They have a different way of doing things. So for the origin of the GRB prompt emission, you have four models, which include optical thin synchrotron radiation from either a random or an ordered magnetic field, synchrotron self-Compton emission, Compton drag models, and photospheric models. So these models show an integrated understanding of the geometry and the physical processes close to the central engine, and it may only be accomplished through high energy polarimetry, since it depends on the emission processes involved in the prompt emission, so very close to where the particle accelerates to high energies. So emission due to synchrotron self-Compton can be moderately polarized, although polarization can be as high as, 40%, depending on the line of sight. But the detection of highly polarized prompt emission would also support synchrotron and Compton drag models as well. So that poses a problem for GRB polarimetry. So it's very close together, so you can't really distinct the models, all these models for GRB prompt emission. So Thomas et al. In the figure here, he showed that a statistical study of a sample of GRBs could then be used to differentiate between these models. So the IC model is inverse Compton model, and the SO model is synchrotron model with ordered magnetic fields, and this SR model is synchrotron models with random magnetic fields. So the fraction of the GRBs with significant polarization is higher for models that have ordered magnetic fields than those with random magnetic fields. So to use high energy polarimetry to distinguish between these models, the polarization measurements would have to be for a sample of GRBs, and which results in a distribution peaking in high. So if it results in a distribution peaking at high polarization, would therefore favor synchrotron models with ordered magnetic fields, for example. Okay, so then we go into blazars. I just wanted to say as well for this, also just a breadcrumb for what I will talk about when I talk about the polarized dependent modeling. So for gamma ray bursts, you also have a few codes that is specifically designed or developed for the prompt emission of gamma ray bursts. And for the structure of the GRB jets as well, you have Landman also have a code specifically developed for GRB jets. Okay, so going into blazars, so this is I would say my favorite. So for blazars, I know a lot more about blazars, so I'm sure that the other models also have a lot of things that you can do with high energy polarimetry that I haven't mentioned. But for blazars, we have a lot of things that we can answer with high energy polarimetry. And this includes the origin of the high energy emission from blazars, particle acceleration in the jet emission of blazars, and also the global jet structure of blazars and GRBs. And then there's also suggestions that you can learn more about quantum gravity from the high energy polarimetry from blazars. So if we, okay, again, just a breadcrumb. Sorry, I forgot about these breadcrumbs. So for polarized dependent modeling, you have a lot of codes and work developed for to help us predict polarization for the high energy emission and for the particle acceleration, as well as the structure of the jet. So yes, you'll see that when I go along. Okay, so for the leptonic and hydronic scenarios for the high energy emission from blazars, so the origin of the high energy peak is less clear than the low energy component, which is usually, we are in consensus that is due to synchrotron emission. For the high energy, it's less clear with two models that is fundamentally different. So the leptonic model suggests that the radiative output throughout the electromagnetic spectrum is dominated by leptons, while any protons are not accelerated to the high energies to contribute significantly to the radiative output. So the high energy component is then from inverse Compton scattering of synchrotron emission or external Comptons. External photons, sorry. The second one, the hydronic models, the high energy component would then be dominated by synchrotron emission of ultra-relativistic protons and cascading secondary particles due to photohydronic processes. So Zhang and Butcher in 2013 evaluated this expected high energy polarization signatures and leptonic and hydronic models, so presenting the maximum achievable high energy polarization degree. And as you can see here, that hydronic models predict higher degrees of X-ray and gamma ray polarization than leptonic models. So it would be easy to distinguish between what the important radiation mechanism is for the high energy emission from blazars if we actually observe the polarization. Okay, so oh, sorry. I think I missed a slide here. So the synchrotron peak of high synchrotron peak blazars can also be confirmed with X-ray polarimetry, since the synchrotron peak extends well into the X-rays. So that can also be observed. I'm missing a slide, but you can also confirm the synchrotron origin of these high synchrotron peaked blazars. Okay, so then the nature of the big blue bump in blazar spectra. So in some blazar spectra, an excess in the soft X-ray and UV regime is seen, in addition to the low energy and the high energy components. And several emission scenarios have been proposed for the origin of these spectral feature and ACDs. So it can either be an additional component from a different region than the low energy component, or it can be, the most popular one would be thermal emission from the accretion disk, but it can also be a Compton emission. And that was the first model that I looked the first model that I used to apply my code to blazars. So I'm just going to show it here, but in the end I'll talk more about that. So I applied my code, the MAPPIES code, which I'll talk to in a little bit, to a model from Barang et al. In 2017, which they modeled the soft X-ray excess as a source of inverse Compton scattering of thermal non-relativistic shock-heated electrons. And in this interpretation, a significant polarization degree would be expected. Okay, so this is just the results from the MAPPIES code, and hopefully I'll have time to go into that in the end. But the MAPPIES code predicted high polarization degrees in the emission region where the Compton radiation dominates, and we also made some predictions of that, predictions for different polarimetry emissions for that, and so I'll get to that in the end of the talk. Okay, so then you can also use high energy polarimetry to constrain the production, to see if to constrain the production of high energy neutrinos in the high energy emission of blazars. So the production of high energy neutrinos provides evidence for hydronic interactions. So if blazars can accelerate enough high energy protons, the protons may interact with the local blazar radiation field and produce charged pions, decay, and emit neutrinos. Okay, so there was obviously the very popular, everybody knows about the IceCube event, and they reported, I think I didn't say it here, it was 1709 something, and that was reported to coincide with the blazar TX0506, I think, TX ACE0506 plus 056. I wrote it down here. Great. So there are models that can explain the neutrino alert, and that can be categorized into two main groups. The first one is a leptonic setup where the inverse Compton dominates. So the high energy emission, the inverse Compton dominates the high energy emission with a subdominant hydronic component. So that's an
only my audio that stopped.
I can't hear either. Lenté, we can't hear you anymore.
I'm sorry, can you hear me now?
Yeah.
I'm so sorry. I don't know what. I'm so sorry. Okay, can you hear me now?
Yeah.
Everyone can hear me. I'm so sorry about that. So I don't know where you lost me, but let me just repeat here. The X-ray polarization degree can probe the secondary contribution complementary to the neutrino detection. So gamma ray polarimetry can be used to distinguish between inverse Compton and proton synchrotron scenarios for the production of high energy neutrinos in blazar jets. So I don't know what you got from that, but so that's all what I want. Yes, of course.
So would it be true that the three models that you have in your plot, the three of them could explain neutrinos? Is that right? The three of them are compatible with neutrinos, or is there one of these three that is not?
No, the three models is compatible. So the one is a pure inverse Compton model, and the second one is the group that has the inverse Compton is dominant with a subdominant hydronic component, and the PS models is a hydronic component with a subdominant inverse Compton component. And both, all of these can explain the production of high energy neutrinos, but the polarization would be different in the gamma ray regime. So we can use that to distinguish between these models.
And can I ask one more thing? So this pure IC model that you have, is there any way, so is this pure IC a model where the hadronic component is not seen electromagnetically? So is there any way to distinguish between a pure IC where there's only leptons and a pure IC where there is enough protons to produce the neutrinos, but you never see the photons coming from the protons?
Well, I think you would have to have a hadronic component somewhere.
So you would see it somewhere, but...
Yes. So one is just subdominant hadronic component. But yeah, this is work done by Zhang et al. In 2019. Maybe Prof. Butcher knows more about this. Prof. Butcher, can you comment? Or do you want to comment?
We can leave it for later also if you like.
Yeah,
No, it doesn't matter.
The pure IC was actually one that did not predict neutrinos.
Oh, okay.
That was actually completely without a hadronic component.
Okay. Okay, so you can use it then to use high energy polarimetry to get that as well.
Thanks.
Okay. Okay, so for particle acceleration, so the particle acceleration in the jet emission region of blazars is also under investigation, and you can have shock models, magnetic reconnection, kink instabilities, also the role of turbulence is also something that people talk about, but I just know about the shock models and magnetic reconnection models since I did research on this for my master's. So since blazar shows multi-wavelength variation, since they show multi-wavelength variation, it indicates that they have strong particle acceleration, and shock and magnetic reconnection both have been suggested as candidates for the acceleration mechanisms. So the shock but these two models have different magnetic field configurations. So the PA swings and multi-wavelength flares is expected in both of the models, but the polarization properties of the blazars indicate that the configuration of the magnetic field is not the same in a newly injected material for different epochs. So modeling the polarization, so we need to account for the variability in order to distinguish between these models. So in shocks, the magnetic field is compressed and thereby increasing the magnetic field while simultaneously producing a flare that might be accompanied by major polarization variations. So that's in contrast to shocks. That's in contrast to magnetic reconnection, so that's in contrast with shocks, where magnetic reconnection dissipates the magnetic energy throughout the topological rearrangement of the magnetic field. Okay, so strong changes in the polarization signatures are not expected during flares for magnetic reconnection, and then for shocks it is. So you can distinguish between shock and magnetic reconnection for these two, for the particle acceleration and blazar jets. Okay, so for modeling, you have a lot of codes. That I just put all the codes here that can help us to model that can do polarized dependent radiation transfer, so help us to model polarization and get predictions for different models. So I always ask why do you want another code or another type of modeling when you do have other models? So if you want to model the polarization for different models, it's very important to take into account the computational time. So to model the polarization, you need to keep it, maybe if I can say, simple and sleek. So a lot of these codes are specifically developed for something. So with AGN jets, with blazar jets, it's also important to know what the source of the target photons are. So a lot of codes is specifically designed to probe that and constrain the source of the target photons, for example. So for Monte-Carlo simulations, so these are the Monte-Carlo simulations, all the other codes are different. I think this one is also a Monte-Carlo simulation. But in any case, so there are a lot of people that use Monte-Carlo simulations to do the polarized dependent modeling for blazar jets or for any source. So this approach is very flexible in the description of the geometry of the medium, or in my case, the Comptonization medium, as well as the distribution of particles involved. So, for example, when you want to constrain the target photon field for blazars, I don't have a picture here now, but for blazars, if you want to constrain the target photon field where you switch over to the inverse Compton regime. So no, I don't have it. So where you switch over from the low energy to the high energy regime, you want to constrain where the target photons come from. So the Monte Carlo, and if you use Monte Carlo methods, you have a lot of freedom with how you describe your particle distributions. So Monte Carlo methods is also very favorable when you consider anisotropic scattering of thermal electrons with different energy distributions. So to study the polarization for different target photon fields and electron distributions. And this can also be, Monte Carlo simulations can also be very easily adapted to different energy regimes. So just what I talked about right now, in order to study the transition from the low energy to the high energy polarization. So I would say, so we're going into the MAPPIES code now, which is the only work that I've done in this presentation, actually. So the MAPPIES code uses a single photon approach, and we use very similar methods than Tambora et al. In the Mocha code, which also use very similar methods than the Monk code. But these two codes are devoted to the spectrum and polarization signatures in the X-ray band for accretion systems. So they study the geometry of the corona to better understand its origins. So that's slab and lamppost models for the origin or the geometry of the corona. So their codes are specifically developed for that, and but so we use the same methods and we follow the same approach from Matt et al. In 1997, but it's used to model and make predictions for different aspects of the physics that we can learn from high energy polarimetry, if that makes sense. So I'm just gonna talk quickly. Yes, I do actually have time. So the MAPPIES code is the code that Prof. Butcher and I developed for Monte-Carlo Applications for partially polarized inverse Compton scattering. So Prof. Butcher was very nice to get me this name because the MAPPIES is my dad's nickname. So he was very clever to translate that to a name for the code. So this is just a schematic overview of the code. You have some model parameters, which is now you can have a lot more parameters, and then you start the Monte Carlo simulation for a single photon. So we do a single photon approach. Most people, I think the Mocha code is the only other code that uses the single photon approach. Most of the time, the people use photon packet approach. So we use a single photon approach, and it just starts in the laboratory frame or the AGN race frame. You draw the direction, that energy, you boost it to the co-moving frame, and then you draw the polarization, you get the polarization properties, and then you also draw the electrons in the co-moving frame. Then you go to the electron race frame, which all of the calculations where the Compton scattering actually takes place. So you calculate the Klein-Ashina cross-section, you ask whether it would be scattered, you simulate that Compton scattering if it would be scattered. If it's not scattered, it just starts again. So if it is scattered, you simulate that scattering in the electron race frame, and then you calculate the polarized dependent. So all these calculations is from Matt et al. From a paper of Matt et al. In 1997. So you calculate the polarization vector, the scattering angles, everything in the electron race frame, and then you just boost it back to the laboratory frame. So that's how a Monte Carlo simulation works. It's very simple to do, and you can have a lot of freedom since you work with predictions and you don't have a lot of constraint, especially in terms of the description of the source and the target photon field, the electrons, etc. Okay, so the code we wrote is written in a modular setup, so it can be applied to different jet-like astrophysical sources in different scenarios, which is very easy to do with Monte Carlo simulations. So the input parameters describes the characteristics of the source, and you can have a lot of input parameters here, depending on what your target photon field is and what your electron distribution is. Well, actually just what the source of your target photon is. So in arbitrary target photon fields, you can have a lot of assumptions here. You can have a monoenergetic electrons, you can have black body radiation or synchrotron emission. It can be unidirectional or isotropically distributed. And then you can also have the polarization status of the photons can either be polarized or unpolarized. Okay, so this means you can have emission from the dusty torus, external emission from the dusty torus. You can also have direct disk emission. So you can also constrain the accretion disk properties in a specific model with Monte-Carlo simulations and with this code. And then for
I just wanted to mention, a lot of us have to leave like at 5 to the next hour. So if you wanted to take some questions, then maybe.
Yes, maybe you can take questions because this is not.
If you still want to talk for 5 minutes, that would be okay.
Okay. It's fine. Okay, so we use the code for a model where the big blue bump emission in blazar spectra arises from Compton emission, and this model was specifically proposed by Barang et al. In 2017. So with Monte-Carlo methods, you can also have input electron spectrums, which makes it easy to use other people's models as an input for the code to predict the polarization properties for that specific model. So just an illustration of that here, we expect for this model, they expected polarization to be significant polarization, and we actually got that from the results. So we have a maximum polarization degree of 48%, and we could make predictions for different polarimetry emissions within that energy regime. And I guess well, that's it. So you can ask questions if you want to before you have to go.
Yeah, perfect. That makes sense. Any questions? We to give the others more time. I start with the question. So for IXPE, will there be one result, or will there be many results? Like if you cut the data set into many different pieces, then you get some time-dependent results.
Well, the time dependent is definitely the next step that I'm going to take with the code. So the code in this, well, the MAPPIES code now, on this stage is not time dependent, so there's no time here, but I would definitely want to make it time dependent and also to study some different jet structures together with the different spectral features of blazars. So for the code now, you can have snapshots, I guess. So for this, for these results, the blazar is in flaring state, and at HESA, the one that I showed with the flat spectrum radio quasar was in low state. So you can have different states of the blazar. You can predict the polarization for high states and low states, etc., different epochs of its lifetime. But time-resolved polarimetry would be very useful for this as well, especially in blazars, I guess. And GRBs, that is a requirement because it's so short-lived.
So for this model that you have on the screen, so you're describing this bump that you see in the X-rays as inverse Compton from the disk photons, right?
No, for this blazar, the seed photons is drawn in the AGN rest frame. From the dusty torus. So.
Oh, okay.
Yes, from the dusty torus for this model. We had another model, and since I do have my thingy here, I can just maybe show you. So I thought I wouldn't have time to show that here. Maybe I can just do this. Sorry. Yeah, so this one was for FSRQ, and for this one, we have the seed photons is from the accretion disk. So since the seed photons is from the accretion disk, the photons enters the emission region from behind, and then high energy component, well, the component that the inverse Compton component is in the UV regime. So for that, Pollux would be a better polarimetry. So for the accretion disk now, because the polarization is in the UV regime, it's quite prominent in the UV regime. It goes down in the IXPE.
Yeah. Okay. Yeah. No. That was exactly my question. If so, the polarization signature would appear anyway if you change the photon field that you are using for the inverse Compton scattering, but it just shifted energy, right?
Yes, it just shifted energy, but also the polarization for the observed spectrum. So that's the solid line. The dashed line here is for the Compton emission. So the polarization for the Compton emission is also very high. But since the target photons is from an unpolarized disk in this case, you have to take that into account. So that dilutes the actual polarization that you would observe. So that's the solid line here for disk photons. So that would be actually lower for disk photons than for the external photons. So photons from the dusty torus, there's you can't see it here because it's the same, but the polarization of the inverse Compton, the high polarization of the inverse Compton is just as high as the observed polarization because you don't have an unpolarized component diluting the polarization. So is that clear?
Yeah, thanks. Yeah.
Okay, and thank you very much for listening.
The other question? One more question. So the results are all kind of viewing angle dependent, so
Yes.
How many sources do you need to have kind of firm conclusions?
How many sources? For blazars, I think you just have to need, I'm not sure how many sources. You have to be specific with the viewing angle, yes. The viewing angle, I think I showed it in this. So the polarization goes, it's very less for other viewing angles than 1 over the Lorentz factor for a blazar. So I did, so a lot of Prof. Marshall and everyone from Reitsox and Beiskopf also told me that it would be very helpful to have a polarization, the polarization in terms of the viewing angle, kind of like a map of the polarization signatures for different viewing angles. But for blazars, this would be less. It would go down significantly for other viewing angles. But yes, you can have the results for different viewing angles. These results are for viewing angle 1 over the Lorentz factor, but you can have, you can get from the code, you can get all the polarization viewing angles, all the viewing angles of the scattered photons. So you can definitely make predictions for different viewing angles, if is that what you asked?
Hey, thank you so much.
Okay.
We can all thank Lenté for a very nice talk.
Yeah, great talk.
Let's stay in touch and we can kind of talk about that fitting model that we talked about.
Yes, definitely. I would like to do that.
But thanks. That's a lot of good stuff.
Yes, and thank you so much for the opportunity.